Welcome back, students. In today's lecture, we are going to go over the spherical harmonic functions, which are the solutions to the quantum mechanical rigid rotor problem we set up in the last class. These functions at first might look a little bit intimidating, but we'll see that we are already very familiar with at least the outline of these functions. So the learning goals for today are going to be to describe these spherical harmonic functions. And as always, we want to compare these functions, as maybe complex as they might be, taking 3 dimensions, to the particle in a box model. We'll look again at these quantum numbers that we talked about last time, L and M sub L, and we'll see a little bit more about how they're related. And then you'll want to be able to be comfortable using these spherical harmonic functions to do things like show that they're normalized, show that find the average position and so forth. So these kind of things that we've been doing for all of our wave functions. All right, so in the last class, we began to investigate quantum mechanical rotation. We looked at the Schrodinger equation, we simplified it, we drew some conclusions from there that both sides must be equal to a constant, we separated the variables and so forth. But we didn't look at the solutions. So today we are going to look at the solutions. Just like for the harmonic oscillator, I'm going to show you how or where the solutions come from. I don't expect you to be able to work with this. I present it to you for information if that's something that you find interesting. So the formula for the spherical harmonic functions, they are the symbol we give them is y, and they are dependent on 2 quantum numbers L and M sub L because there are 2 dimensions in play for rotation. Now, the first part of this equation, just like the first part of our harmonic oscillator equation, is a normalization constant, albeit this one is much more complicated than for the harmonic oscillator. But here, all we have are our quantum numbers, and this gives us a normalization constant out front. Then we have 2 functional parts that are, again, separate variables. So I'll talk about this one first because it's simpler. We have an imaginary exponential based on the quantum number M sub L, and the variable phi, so that angle there. For the theta variable, we have a polynomial. So this part here is again, it's more complicated. I wouldn't expect you to be able to make these polynomials. The polynomials are in fact solutions to this differential equation down here, but they are just a list of polynomials. And just like for our harmonic oscillator, our polynomials are actually functions of cosine of theta rather than functions of x. So our first polynomial we'll see is just x, so it's a cosine theta. And then we get more complicated polynomials, then we plug in cosine theta in there, and we get a variety of other trigonometric functions. So we'll see, in the solutions, they won't look like polynomials because they're polynomials based on cosine of theta. All right, so with that out of the way, let's actually look at some of these solutions. So here are the first few solutions of the spherical harmonic functions. This first one, when there's a quantum number 0 and 0, we just have 1 over the square root of 4 pi. And there's no dependence on that. That's just a constant. In spherical coordinates, that means at every angle we have the same value, which is then a sphere. So this first function represents a sphere. All the other functions are more complicated. And you can see that if M sub L is non-zero, so if it's positive or negative 1, we have imaginary exponentials here. So we have imaginary functions. Now that can be, problematic for us as we're trying to imagine what these imaginary functions are. And so the way that we get around that is by taking linear combinations of these imaginary functions. And we'll see how that happens here. So at this point, I imagine you can't look away from these. These are showing you things that you already have seen before, px, py, pz, and then all of these d orbitals, I'll call them that now. But we can see that what we do here, so for example, the px orbital is we take a linear combination. So in this case, we subtract y1, y11, and y1 minus 1. and then we multiply by -1 over the square root of 2 as our normalization constant, and we get this new function that is only a real function. So this normalization constant here ensures that our function is still normalized, so the area under this function is still equal to 1. And we also have, again, a different normalization constant for py. Again, remember that our normalization constants can, of course, be imaginary, and that's okay because only the square of the magnitude matters. So this gives us a function that has sine theta cosine phi, or sine theta sine phi, or in the case of pz, just cosine theta. These new functions, so these px, py, pz, and also all these d functions down here, are still an orthonormal set, just like our eigenfunctions would be, and they are still solutions to the Schrodinger equation. So if you plugged in the square root of 3 over 4 pi sine theta sine phi into the Schrodinger equation that we set up for the rigid rotor, we would still end up with a constant that corresponds to the energy level there. Although it would be a little bit more complicated, again, because we have these trigonometric functions, but they're still viable solutions. Now, if we wanted to plot what these equations look like, we would get, as we imagine, the orbitals shapes. So we remember these shapes from orbitals. We have px pointing in the x direction, pz pointing in the z direction, py in the y direction, and then we have these funky d orbitals, including this dc squared, which has this nice loopy thing here. Now, I want to stress at this point that we are not yet talking about orbitals. It's hard to separate this from the orbitals because we know the orbitals so well. However, we are missing one major component, and that is that these are rigid rotors. So there is a constant radii for all of these functions. We're not yet asking the question, where is the electron around the hydrogen atom, where we allow the radius to change? We're asking, how does our molecule rotate? And so that, again, is a major difference here. What we'll see is that if we try to apply this, when we apply the Schrodinger equation to the hydrogen atom, we'll get some rotational angular dependence that has the same functional form as our spherical harmonic functions. And we'll see that in a couple weeks when we talk about the hydrogen atom. Another thing to note is that our functions also have nodes, just like the particle in the box model. So for the particle in the box model, you remember that as the n increased, as the quantum number increased, we introduced more nodes. So the first function for the particle in the box has no nodes, and then it has 1, 2, and so on. That is the exact same for a spherical harmonic function. So the lowest energy level corresponds to L equals 0, and that is a sphere with no nodes. The next highest energy level is L equals 1, and that gives us these p orbitals, where we have one planar node here, and it depends what plane it's in based on the orientation of the p orbital. And then as we go into the d orbitals, we can see that there are 2 nodes and so forth. So we increase in nodes for our spherical harmonic functions, for our orbitals, in the exact same way as we increase in nodes for the harmonic, or for the particle in a box. So in general, we can see that as the energy increases, the number of nodes associated with that energy increases. And we kind of learned about this for the orbitals. And here we can see, again, quantum mechanically, where that comes from. I want to point out another interesting thing is that if we were to add all of these together, we restore spherical symmetry. So here, this is a combination of all the p orbitals, and here a combination of all the d orbitals. It's a little hard to see with the way that these orbitals are described here, but if we added all the p orbitals together, we would have a sphere. And if we added all the d orbitals together, we would have a sphere, just like for the s orbital, which it makes sense when we're talking about rotation here. The last thing I want to mention is that the shapes of the orbitals can be a little bit misleading. This is just the possible angular locations of our rotating molecule, again in wave form, so it can be hard to imagine. But the position is not uniform. So if we bring up this probability density, in this picture, black is more likely than red. So we can see that we are much more likely to be rotating near this Z plane. And we don't really see that from this shape, but when you plot the probability density, like the magnitude of the shape, this is just plotting the shape itself, the magnitude of the shape, we see that we're more likely to be in the z plane. And you could do the same thing for the y and the x orbitals and these fancy d orbitals as well. So now I want to go over pretty briefly the energy levels of the rigid rotor. We talked about these last time, and I'll just mention them again here. Remember that the boundary conditions for our 3D rotation is that we have to be single valued for our functions for theta and phi, and we also have to be normalizable over our dimensions. So this gives rise to the following quantization conditions, where our beta, which remember is our energy, is dependent on the quantum number L times L plus 1. Again, only the quantum number L, which is a quantization of the angular momentum for these modes. M sub L is the z component of the angular momentum, and so it depends on L, and we'll see a little bit about that at the end here. So our energy in this case is equal to the following. Again, it's only dependent on the quantum number L, and it's equal to h bar squared over 2I LL plus 1. And this will give us our energy. Now, remember, it's not dependent on M sub L, unlike two-dimensional rotation, because for two-dimensional rotation, the angular momentum was completely described by the z component of the angular momentum. So L was equal to M sub L. In three-dimensional rotation, there are two other components to the orbital angular momentum, and so the M sub L is not enough to describe the total angular momentum. I want to point out one other interesting thing, and this is going to go along with why we care so much about these quantum numbers L and M sub L. So for three-dimensional rotation, we can always describe the energy as the square of the angular momentum divided by 2 times the moment of inertia. And we talked about this in the last lecture. This is a direct, comparison from linear momentum and energy. Now, what that means for us is that we could have a total energy operator that would give us the total energy. And we could also have an operator that's the square of the angular momentum that gives us the square of the angular momentum. And the difference between those two would just be this constant 2I. And going into what we talked about commuting operators, that implies, and it's true, that if there's an operator for L squared, that commutes with our total energy operator. Since the only difference between these two operators is a constant, we could operate on our wave functions with both h squared and L squared and return two constants that are very similar, and we could know both of these at the same time. So that means that we have this L square operator, and instead of giving us h bar squared over 2I LL plus 1, it gives us h bar squared, times LL plus 1. So there is a total energy operator at L squared, and it commutes with the total energy. So we can know the total energy, and we can know the square of the angular momentum at the same time. Now, we can't actually know the angular momentum. So the operator L does not commute with the total energy operator. But since we know the L squared, we could take the square root of this and get the magnitude of the orbital angular momentum shown as L here. So we don't know what direction it's pointing in, but we know how long it is. And we could also try to evaluate all of our various dimensions here of our orbital angular momentum. And so there are orbital angular momentum operators, and they are shown here for Cartesian coordinates. It's much simpler to think about them in spherical coordinates. So we'll go ahead and do that. And what you might be able to notice right off the top of your head is that this L sub z is much more compact than the other two. And I want to stress that there's not really a reason why L sub z is chosen, right? I mean, it's arbitrary. But what this does show is that we can't know all of the components of the orbital angular momentum. You could try to show this, or you could just take my word for it, that Lx and Ly do not commute with L squared and the total energy operator. However, LZ is just a simple derivative with respect to phi, and we can show that this does commute with our total energy operator, and that makes sense because our phi dependence of our wave function is simply e to the IML phi. So we're just going to return IML when we take a derivative with respect to phi. These other more complicated ones are, of course, going to be a little bit different. So what does this mean? It means that if we wanted to, we could know the total energy of our rotating particle, and we could know the magnitude of the orbital angular momentum that comes from L squared, and we could know the Z component. So we can know one of those components. However, we cannot know all of them. So we can know these three things all simultaneously. And as we apply this to orbitals, what we're going to find is that we can know the energy, which comes from the quantum number n, the orbital angular momentum, which comes from the quantum number L, and the Z component, which comes from the quantum number m sub L. So these n, L, and m sub L quantum numbers are going to be very important for our atoms, our hydrogen atoms. And these are the quantum numbers that we can know because their operators all commute with each other. So with this information in mind, we can understand a little bit about the origins of our hydrogen atom orbitals a little bit better. Now, knowing that m sub L is dependent on the Z component of the orbital angular momentum, this allows us to kind of see where it comes from and why we have this quantization that's dependent on L. So we'll go into that here and we'll ask, well, so for L equals 2, what are the possible values of m sub L? And you guys know this from thinking about the hydrogen atom in Gen Chem. You know that if L is equal to 2, m sub L is equal to -2, -1, 0, 1, or 2 is one of those options. And we can evaluate this by determining their relationship. So if L is the square of the orbital angular momentum, or determines that, then what can we say about the Z component? So again, remember that the length of our orbital angular momentum is h bar squared times the square root of L plus 1. And if we plug in L equals 2 to that, we get a length of 2.45 h bar. So our LZ, right, the Z component of our angular momentum is ml times h bar. So if the total length of our orbital angular momentum is 2.5 h bar, we can see now why the length of our Z component can't be greater than 2. If it was 3, then it wouldn't make sense. We'd have one component that's longer than the length of our vector. So our ML quantum number that determines the length of the LZ part of this vector must be 2 or lower. Of course, it could also be negative because we're talking about a vector. So this gives us some limits on what our variables are. And of course, these would be best thought of as cones because we're talking about rotation here. And here you can see the possible values for mLs of -2 to 2 here. So hopefully this allows us to better understand why, these weird restrictions on m sub L, why it has to be -L to +L in integer steps. And the integer steps, again, come from the fact that it's this quantum number comes from the solution of the Schrodinger equation. Before I end here, I want to mention the total energy. So we've talked now about translational degrees of freedom with the particle in the box, vibrational degrees of freedom with the harmonic oscillator, and rotational degrees of freedom with the rigid rotor. And each of those gives an energy level. Now, we can say that the total energy is simply going to be the sum over all of these various energy values. And now when we're doing this, we're making a pretty big assumption that these energy levels are uncoupled, that they're independent, so that the vibration has no effect on the rotation, right? We have a rigid rotor, we have a harmonic oscillator, and so forth. Now, that assumption is not strictly true, and we'll evaluate some of this in our labs. We already have evaluated some of this in our labs, but this is often pretty small, the deviations from this assumption. And again, the last thing that we can see, and we've seen this kind of stuff before, is that when we sum up the energies, that's implying that our wave function is going to be the product of these various variables. So our total wave function would be a product of the translational degrees of freedom times the vibrational times the rotational. And we could also throw the electronic in there as well. We haven't quite talked about that yet. So to conclude this chapter, we use the Schrodinger equation to give us the eigenfunction solutions to the harmonic oscillator problem and the rigid rotor problem. And we can use these to model quantum mechanical vibration and rotation. Our harmonic oscillator assumption is a pretty good approximation for small energy levels for vibration. And the rigid rotor, again, is a pretty good approximation for rotation. If we wanted to be more exact, we would need to consider slightly different functions, but we're not going to do too much of that in the course of this class. We have a quantization in the energy levels for both of these types of degrees of freedom. Again, the rotational energy levels are degenerate. We can't distinguish between things like the p orbitals or the d orbitals, so we have different types of degeneracy there, and we'll talk about that in the next chapter. And we can sum up all of the energies to talk about all the total energy of a particle. In the next chapter, we are going to take these ideas that we have for vibration and rotation and apply that to spectroscopy. So we'll see that if we excite molecules with energy that corresponds to the change in energy between the ground state and the excited state for vibration, we can promote a transition to the excited state, and we can actually see vibration. And the energies at which this happens for most molecules are in the infrared region. And when we excite these transitions, we'll see that rotational transitions also come along with it. So we'll talk about how we can apply these ideas to rotations starting in the next lecture.